So hello, we are now in week number 7. So this will be class number 13. We're going to start by going over the exam. So it says, write a sample space with equally likely outcomes to the situation of rolling 2 tetrahedral dice, each of which has 4 faces, number 1, 2, 3, 4. So this is kind of like the situation we did with 6-sided dice, where you just list every possible pair of numbers. Remember, a sample space are the possible outcomes, right? So the possible outcomes would just be the 16 possibilities, dot, 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 of course, on your test. Hopefully you didn't do dot, dot, dot. You actually wrote them all out. But there's 16. The sample space is those 16. Technically, you should have put them in parentheses, but I really wasn't focusing too much on that, so I didn't take off anything if you didn't. Right? Well, that's nice and straight. Anyways. Then it says construct a probability distribution for the difference of the 2 tetrahedral dice. First die minus second die. So 1 minus 1, this one gives me a 0. 1 minus 2, this one gives me a -1. And in fact, it even says you're going to get negative differences. 1 minus 3 is -2. 1 minus 4 is -3. 2 minus 1 is +1. 2 minus 2 is 0. And you go through all of them. You don't got to put the numbers here. I'm just listing them here. But then it wants a probability distribution, right? So then you list all the possible outcomes, for example, -3. And how many times is -3 possible? Well, the only way of getting -3 is to get a 1 and a 4. So that's a 1 in 16 chance. And then when I go to -2, I see there's 2 ways of getting a -2, either 2 and 4, right? Or 1 and 3. So that's going to be a 2 in 16 chance, or 1 in 8, and so on, right? So this was nothing new. We've done those before. I got to exit out so I can scroll up. And then I got to erase them, I'm sorry. Clear, oh my gosh. So then we go here. What is the probability you roll a difference of 0? Well, you can just think about that. How many of the 16 ways can you roll a difference of 0 if they're doubles? So there, by the way, wonderful tetrahedron. I love it. Very nice. But to roll, in fact, yeah, that's great. We should spot like your video. You can just be my sounding board here. So what is the probability that you roll a difference of 0? Well, how many ways can you roll a difference of 0? There's 4 ways: double ones, double twos, double threes, and double fours, for a total of 16. How do you, yeah, add spotlight there. I don't know if that worked or not. And then what's the probability that you roll a difference of 2 or more? Well, 2 or more, that could be a 2, a 3, or a 4. No, you can't get a 4. That's 2 or a 3, right? 2 or more, 2 out of 2 or 3. How many ways are there of getting a 2 or a 3 as a difference?
4 out of 16.
So it should be
1/4.
what, 4 out of 16, right? Yeah. I don't know how to get it. Let's see. To get a 3, it's a 4 and a 1.
16.
It's 3 out of 16, right?
Difference of 2
Yeah,
or
3.
more?
Huh?
A difference of 2 or more?
Difference of 2 or more means a 2 or a 3, right?
3.
3 over 16, isn't it?
Say again.
3 over 16?
3 out of 16. It should be 3 out of 16, right?
How is it 3? Isn't it 4?
Well, how many ways can you get a difference of 2?
2.
And how many ways can you get a difference of 3?
1.
Well, that's 3 total, right?
Oh, I miscounted. That's why.
Okay, so that's number 1.
For number C, you said it was 4 over 16, or what was the answer for number C?
4 to 16, yeah.
4, okay.
Because there's 4 ways. There's 4 ways of getting a difference of 0 out of the 16 possibilities, correct?
Yep.
Okay. Question 2, your students flip a fancy, this is exactly like one of the homeworks, exactly like the quiz. Your students flip a fancy button calling one side outside and the other side inside. The first 6 flips are given by there. So we want to do the results. So the results are outside, outside, inside, outside, inside, outside. How many outsides are there so far? 1 out of the 1 flip, 2 out of the 2 flips, still 2 out of the now 3 flips, now 3 out of the 4 flips, still 3 out of the 5 flips, and finally 4 out of the 6 flips were outsides. So 1 is 100%, 2 is 100%, 3 is 2/3, about there.
Professor, if we did this in decimals, that's fine too, right?
Yeah, that's fine. That's fine. 3 is about there. 4 jumps to 75%. 5 is down to 60%. And then finally 6 is there, right? So
Okay, that's good.
okay, something like that. What is your estimate of the probability that the button lands outside? Well, it's your final value, 4 out of 6. Can't beat 4 out of 6. It is using every piece of information that you were given, i.e. all of your flips. Does that make sense?
Yes.
So again, that was like a homework and a test question. Question 3, fill in the missing words to describe the law of large numbers as it is applied to flipping a fair coin repeatedly. Yeah, Victoria, I have you in the mirror. I'll change it when I have a chance. Fill in the missing words to describe the law of large numbers as it is applied to flipping a fair coin repeatedly. As the number of flips increases, the proportion of heads approaches 50%. It's a fair coin, so it's a 50% chance. As the number of flips increases, the proportion of heads approaches 50%. Does that make sense?
Yes.
If you wrote the true probability, I took off a few points because then you're not using this problem at all as it is applied to flipping a fair coin repeatedly. You're just using the law of large numbers, but it's also for flipping a fair coin. You have a class of 10 students. How many different ways can they line up single file? Well, they're all rushing to get into the line. How many people can be first in line?
1.
Well, 1 could eventually be first in line, but I mean is how many options do we have for who's
10.
first in line? 10. And once that 1 has been chosen, how many options do we have for who's
9.
second? 9, and then 8, and then 7, then 6, 5, 4, 3, 2, 1. And then by the fundamental theorem of counting, we multiply. So the answer is 10 factorial. Right?
Right.
Wouldn't it be like 10 to the 10th power because
No, each
10 different students can be up like
yes, but once the first student has taken the first slot, that student no longer has a possibility of being in the second slot. Right? If you look at Solaire's board there, Solaire's being wonderful. I will donate half my salary to her for.
well like no that's what I thought, but then it didn't say like that person stays at the front, like each person like stays.
Well, I mean, that's kind of assumed. It's, you're lining up single file, right? Once you get in line, you don't leave line and make a new line or anything like that. There was no trick questions here. Just a basic single file, 10 options, 9 options, 8 options, 7 options, and so on. How many ways can you pick 2 of the 10 students to be ball monitors? Well, when you pick the 2 ball monitors, the first question you have to ask is, do I care what the order is?
No.
Is there an order to it? No. So this is a, what's the word?
In.
Combination. N is, yes. N is what? What's my N in this example?
10.
10. And what's my R?
2.
2. Do the math, you get 45.
Son of a-
Son of a bitch, right? Do the math, you get 45. 10 factorial over 8 factorial, 2 factorial. Part C,
Sorry.
it's okay. I've heard it before. Parts, of course, it is on video. So part C is the easiest and yet probably was the one that people scored the worst on because you were just expecting to be some kind of factorial problem or a combination problem or something. It says if you assign a math worksheet that has 20 problems and give a spelling quiz that has 15 problems, how many problems we have to grade? Well, each student is answering 35 problems, right? And there's 10 students, so 350.
I was confused on why you put that in the test, but I just went with it.
I put that on a test because I wanted to differentiate between those who kind of just aren't
Overthink?
they don't I don't know if overthink's the right word. Sometimes when you have some formulas, you try to force a problem to fit a formula, and you don't just do the problem as it is. And in math, you should never try to force a situation, right? You look at the problem and say, what do I need to do this one? And well, some people did, some people didn't, but that was the point. Anyways, question 5 was the hardest. There's no question about it. Question 5 was the hardest. Okay. So a class has 47 male students. Hold on, I want to do the other annotate method. How do I? How do I annotate this?
You go to view and show markup toolbar. Or edit. No.
It's been here before. Oh, maybe it's not.
You need to open it separately from Canvas, I think.
From Canvas, really?
So download it and open it in your.
Oh, that's right. That's right. Okay.
Yeah.
All right. I don't know how to do that anymore. So, okay, I'll do it next time. Okay. So a class has 47 male students, 38 of whom have jobs. Go away. And 53 female students, 40 of whom have jobs. Make a frequency table. So this is a two-way table. So where I want to copy yours. So where are you going to put male, female, top or the side?
Top.
Top. Okay, male, and then female. Okay.
Yeah.
Okay, and then we'll have working or not working. Okay. So a class has 47 male students, so there's 47 males in total. And 38 of them have jobs, 38 of them are working, and therefore 9 of them who are not. And it has 53 female students, 40 of whom are working, and therefore 13 of them who are not. And then we have the totals for the rows as 78, 22, for a total of 100. So first, what is the probability of male and working? So before I even worry about the numerator, it's going to be over 100. The last one, male or working, over 100, because they're both looking at everyone. Now, male and working, how many of the 100 are males and working? 38. Just these guys. Now, males given working. Since we're given, how about 4A? Did I skip a problem?
No, I just didn't write it down, but they're helping me in the chat. So.
Oh, okay, okay.
Yeah.
Males given working. So since it's given working, I only care about the 78 who are working. No one else matters, just those 78. And of those 78, how many are males? 38. And working given males. So of the males, well, there's 47 males. And how many of those 47 are working? 38 of them. So 38 over 47. Male or working, count this, count this, count that. Because these are males, those are working, and I'm happy with either one. So when I add them up, I get 87. 87 of the people are either males or working, or both. So that was it for part B. Then it said in this class, is a male more likely, less likely, or equally likely to be working than a female? So this one is the one that tripped people up the most. What exactly do we have to compare here? We have to compare of the males, which there's 47 of them, how many of them are working? 38 of them. And of the females, there are 53 of them. How many are working? Well, 40 of them. And which one of these is greater? So the males is greater. Males are more likely to be working than females.
Professor, I have a question.
Yeah.
Back on the probability of male or working,
Yeah.
I got the same answer. But I was wondering if it's gonna work every time. The way I did it was I took the 38 and 40 and the 47 and I added all those. And then I subtracted by what we counted double, which was the 38, and it gave me 87.
Yeah, that's
But is that what would that work every time if I
yeah, 100%.
Okay.
Works every time. Every time. Okay, anyways. So then we go to the last one, which is 4D. It says, in this class, are the variables gender and working or not working independent categorical variables? Answer this question. Justifying it. So, thank you so much. You're awesome. And it's, the exits are on that side of the plane and that side of the plane. And, you should be one of those people. Anyways, in this class, are the variables gender and working or not working independent categorical variables? Answer this question, justifying your answer. So I already deleted it. So let's highlight Solaire's video. I'm going to stop sharing and highlight hers. Oh my God, we're like equal. So in order for this to be independent, we would look at 38 over 47 and compare it to 40 over 53, which we've already done. Because those are not the same, then
gender plays a role.
Then gender plays a role, and therefore they are dependent. Anyway, that's a test.
If I were to put non-independent, is that the same thing?
Non-independent is the same thing. Yeah, that's fine. Yeah, you can either do it as independent or as dependent.
So they're dependent because they don't affect each other.
No, they're dependent because they do affect each other. One depends on the other.
How so?
Well, you can see that there's a difference in probability depending if it's a male or a female. If it's a male, it's 81%. If it's a female, it's 75%.
Okay, so if they were the same, they'd be independent.
If they were the same, they'd be independent.
Okay, I get that now. Thank you.
Yeah.
Wait, so if we wrote, I'm sorry, that was confusing. If we wrote not independent, is that wrong?
Not independent is fine. That's the same thing as dependent.
Oh, okay, sorry.
That's okay.
Professor, what if I wrote not independent because they're not proportionate numbers, but I compared the wrong fractions?
It depends on, there's just more than one fraction method to see whether it's correct or not.
I did 38 over 78 and then compared that to 9 over 22.
38 over 78, that works too.
Okay.
It makes no difference whether it's this way or this way. So that works. Well, there's more than one possibility.
Okay, thank you.
Okay. Anyway, are there any other questions?
So for 5C, we just have to like do the fraction, right? Do like 38 divided by 47. That's how we would figure it out. To get like 81.
Well, you got to compare it to 40 over 53.
Yeah. Okay. Because I did the long route for some reason. I multiplied both things by each other. So I did 47 by 53 and then 53 by 47. And then for the numerators as well, I got like this big old number. And I compared which one was bigger. That's how I found out. But I didn't know there's a simpler way.
Oh, also to make a comment on what someone said earlier, I don't think it's 38 over 78 and 9 over 22 because that's only looking at male. You'd have to do 38 over 78 compare it to 40 over 78.
Well, no,
No,
it's,
never
it's,
mind. Never mind. Is that correct? If you do 38 over 78 and 9 over 22?
you 38 over 78, 9 over 22, or 38 over 47, 40 over 53,
Okay.
or 9 over 47, 13 over 53, right?
Okay.
Anyways, any questions? All right, well, let's start with, you'll get it back. Well, you won't get it back, but I'll grade it as soon as I can, hopefully next week or this weekend. But let's go ahead and let's start with number 8. So let's do it. Okay. How do I can't minimize this when I'm sharing, but I can do this. Okay. So where do I have it?
Oh, you have to unpin me also, Professor.
Oh, okay.
Or remove pin.
Move spotlight, okay. And then let's take a look. Here's 8. Okay, so please load up number 8. I'll load up, I'll start sharing my screen as well. So let's go ahead and do this. Okay. It goes randomness, runs, and coincidence. Okay. Class activity. Let's take a look. Look over the 2 sequences below. One of them was obtained by tossing a coin 200 times and recording from left to right and line by line the sequence of heads and tails. And the other sequence is fake. So guess which is which, giving your reason. So take a few minutes and see if anything stands out as a reason why one of them might be fake. By the way, who's not on mute? There's someone who's making lots of noise. Okay. Anyone have an, I think I have something. I don't know if it's right or not, but I think I have something. Anyone want to give it a shot?
I think the second sequence at the bottom, because I'm looking at the third row, and it's H H H H T H T T T T T like 5 times in a row, and then H H H like 5 more times in a row.
Okay.
And it just keeps on recurring in that fashion.
And that would mean it's fake or not fake?
That is fake, because it just seems very improbable for it to do that.
So it's
based on what we've learned.
Yeah, it's actually interesting you say that, because that's the exact reason why I believe that's the right one.
Oh, wow. Okay.
And I'll tell you why. Because if things are truly random, then you should expect to have streaks every now and again. And if you don't have any streaks, that's probably less likely than if you do have streaks. The first one, I don't see any streaks anywhere. I see 4 at the most together.
Yeah.
Let's take a look at their
Like no more like 3s and 4s, but nothing more than what it's like.
Nothing more than 4. And if you're doing it fakely, you'd probably start to think, oh, I can't have too many in a row. So once I've had 4, I better switch.
Right.
Right? But if it's truly random, then you should expect to have streaks every now and again.
Oh, never considered that.
Right? Does that make sense? And that's what they mean by a run, right? A run is a sequence of the same outcome. Okay, so let's take a look. Most people classify the sequences above incorrectly because they don't have a clear idea of what random means. Which of the following is the best interpretation of a random sequence of events? 1, the events follow an unusual order. Or 2, the different events in the sequence are thoroughly mixed up. Or 3, I guess is a little font issue. Which event occurs next has nothing to do with the events that occurred before it. That's number 3. There's no memory to a flip of a coin. The coin doesn't say, oh, we had 4 heads in a row, we better throw in a tails now, right? Every one is as equally likely to be heads or tails as the next one, right? So which event occurs next has nothing to do with the events that occurred before it. That's truly what random means. So when people are asked to write down a random string of letters or numbers, they tend not to repeat the same item very many times in a row. Sequence 1 above, for instance, is very typical of what students will construct if asked to simulate 200 coin tosses by writing 200 random heads and tails. As you may have noticed, the sequence never has more than 4 in a row. It can be shown, we're not going to do it, but it can be shown that this would happen in a truly random sequence about 1 in 500 times. So in a truly random sequence, you got to expect to have streaks. And the reason people are poor at recognizing randomness is due to 2 closely related erroneous beliefs known as the law of small numbers and the law of averages. So go ahead and read the law of small numbers and the law of averages, please.
You want us to read the definition of the law of small numbers?
To yourself, to yourself. So the law of small numbers. People often think that even small segments of sequences should reflect the overall proportions. But remember what we did with stabilization, right? What do we always say about small trials versus a large number of trials? When does stabilization occur?
After a large number.
After a large number. You never expect to have small segments reflect the true value. And that's the law of small numbers. Okay, people think that even small amounts should reflect the overall proportions. You're always going to have major fluctuation in the beginning. What does the law of averages says? This says that when events go too much one way, there's a tendency for the events to go the opposite to balance things out. But these are both wrong. This is not true. The law of averages is not true. The law of small numbers is not true. The reason why things balance out is because the law of large numbers, not the law of averages. Okay, it's not, there's no force in nature trying to balance things so that if you have a lot one way, oh, we got to make a lot more the other way to balance it out. It's just that the law of large numbers says that as the number of sequences increases, you approach stabilization. But there is no law of small numbers and there is no law of averages. These are both, you might even have heard the term, oh, the law of averages. It doesn't make sense. There's no such thing. There is no law of averages. There's a law of large numbers. So these 2 laws make people think that a sequence that has long runs cannot be random, but it's just the opposite. Truly random sequences will always contain runs if they are long enough. By the way, what's the name of the correct law that describes how things balance out?
Law of large numbers.
The law of large numbers. So what is the correct scenario? What do you expect to actually happen? You're going to have lots of H's. You're going to have lots of T's. Sometimes one in a row, sometimes two, sometimes three, sometimes four, sometimes five. It could be all over the place. All we know is that in the long run, it'll reach stabilization by the law of large numbers. Okay, but these two things, they just don't make any sense at all. Yeah, so their question?
That's kind of like how your GPA averages over time.
So you're saying sometimes it goes up, sometimes it goes down.
It's so if you take one class and you get an A, your GPA is at a 4.0.
Right.
And if you take another class based on the number of units too, and you fail that one, now your GPA is at like a 2. So as time goes on, your GPA doesn't fluctuate as much because you have more units accumulated and it stabilizes no matter how many A's you get after a certain point.
That's true, 100%. See, it's the proportion that matters.
Yeah.
Remember that in the test question, it was 1/1, 2/2, 2/3, 3/4. The bottom keeps going up by 1 every time, which means whether the top goes up by 1 or is not, because the bottom is going up, the numbers are more and more likely to reach a certain value because they're not going to fluctuate as much, right? Because 99 out of 100 or 100 out of 101 is essentially the same number, right? Take out your calculator. 99 out of 100 is, of course, 0.99. That doesn't really require a calculator. But 100 out of 101 is also approximately 0.99. It went up by the 5th decimal place. Whereas 1 out of 2 and 2 out of 3 are very different. So as the denominator goes up, it has less and less of an effect. Very good. That's a great, astute observation. So use the following approach to predict how long the longest run of consecutive heads is likely to be in 200 tosses of a coin. A. First note that a run of heads starts after a tail. Okay, you can't start a run of heads in the middle of a run of heads. It's got to be either the very first toss is a head or tails and now I have a head, right? So the start of a run of heads comes after a tail. How many opportunities are there in 200 tosses of a coin for a run of heads to get started? Right? How many opportunities are there in 200 tosses of a coin for a run of heads to get started? Well, I expect to have 100 tails, correct?
Yeah.
So after every single tail, I could start a run of heads, right? So if there's 100 tails, or I expect 100 tails, then I should expect to get 100 possibilities for a run of heads. Does that make sense? Yeah. Every tails leads to a possible run of heads 100 times. Now, of those 100 possibilities, half of them are going to be tails. Right? Because I expect half of them to be heads, half of them to be tails, correct? Right? So of those 100 possibilities for a run of heads, how many actual times am I going to have 2 heads in a row? Or should I expect to have 2 heads in a row? At least.
Half of that.
Half of that, which is 50.
Yeah.
And half of that should be how many I have 3 in a row, which is about 25. And half of that should be 4 times in a row, which is 12.5. And half of that should be 5 times in a row, which is 6.25. So I really should have 6 opportunities for a streak of 5 heads. This is just the idea. We don't got to go through the actual math, but this is the idea that there's plenty of opportunities for a streak, more so than you would expect. Does that make sense? Yes, no, maybe so?
Maybe.
Well, maybe we should do it. Maybe we should do it. So let's actually go through it then. Maybe we should do it. So it says, again, it says a run of heads starts after a tail. Since I expect to have 100 tails, I'm going to have right 100 tails out of my 200 tosses, correct?
Yes.
That's how many tails I expect. Correct?
Yes.
Now, of those 100 tails, the next one is equally likely to be a heads or a tails, correct?
Yes.
Okay, which means I should have 50 chances, I guess, for a streak of heads to start. Right? I have 100 tails. Each one of those tails will either be a tails or a head following. So if I have 100 situations of a tails, I should have 50 situations where a streak of heads can start.
Yeah.
Now, of those 50 heads, how many of them do I expect to follow with another head?
25.
25 of them. So I have 25 chances for 2 heads in a row. And then after that, how many situations do I expect to have? Do I have 3 heads in a row?
12 and a half.
About 12.5. And then how many for 4 heads in a row?
6.25.
And then how many for 5 heads in a row?
I can't do it that far.
3 point something. Right? 3 point something, right? So that means I should have roughly 3 times where I have 5 heads in a row. But if you were doing them at random, just one after the other, you probably would have no heads, 5 heads in a row, right? Because, oh, that's not random. That's too many in a row. But the whole point of this exercise, and we don't got to go through every step because it's a long, lots of steps here. But the whole point is that you have lots of opportunities, more so than you would expect. Does that make sense?
Yeah, that's better.
Okay. So the human brain is also built to notice patterns and ascribe meaning to them. The basic lesson from the class activity above is that humans perceive the short-range patterns that occur naturally as being meaningful. Okay, but short-term patterns are never meaningful because they are the result of random fluctuations which always occur in the short run. In addition to long runs, you may have noticed other patterns in sequence 2, such as THHH, 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 THHH. All right, according to that happens 4 times. Let's find them. What did they say it was? Line, what was that? That was line 5. So let's take a look at line 5. TTTHH, TTTHHH. So here we go. Right here. Annotate. So we have THHH, 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 THHH. 4 in a row like that. You might say, well, that's not random. That's too systematic. But the whole point is that if you have a long enough pattern, you're going to have, I guess we can call them coincidences, occur significantly often. Things that do not look random, but actually are. So all the reasons that you would reject sequence 2 are the reasons why sequence 2 is actually the correct one. It's just, it's very natural to get that wrong. Does that make sense so far?
Yeah.
Any questions on that? Okay.
Professor,
Yes.
well, looking at the first 10 flip,
Yeah.
would it be possible to figure out if that's also a true sequence, the first 10 flips?
The first 10 flips, like here at the top here,
No, for sequence 2.
for the first 10, H, H, T, 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 H, T, T, H. I don't know. I don't really see anything here that would throw me off.
Because I mean, for those first 10, it's a 50-50. They were all 50-50, right?
Yeah, but if you got H, H, T, 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 H, T, T, H, H, would you say this is not random? Would you make that conclusion? No, I don't see anything here one way or the other. It's not until I really see a lot of them, like right here. That's what, 7 T's in a row? Right? If I was making my own sequence and I said, okay, let's make a random sequence, I would never throw this in. 7 T's in a row. But it's just the opposite. Especially because I had 5 T's in a row shortly before that, right?
Yeah.
In the middle of that, I had what, 6 H's in a row. So these are things that are going to occur. But if you're trying to be random, you would never have them there because they don't look random. So it's exactly the opposite.
So
that make sense?
so then sequence 1 is the fake one then.
Sequence 1 is the fake one. That's correct.
Okay.
Yeah, sequence 1 is the fake one. Okay, so what is this? How much more do we have? I'm so tired right now. Oh, not that bad. We could probably finish this. Okay. So then it says, let's see, do I want to do this? Let's see. When the iPad Shuffle first came out, it generated playlists by randomly choosing songs from the user's music library. Many people complained that when a new playlist was generated, the iPod often seemed to pick the same songs as before. So Apple had to come up with a modified algorithms that made the selections less randomly in order to resolve the problem. In other words, the issue is that if it was truly random, then you should expect to hear the same song 2 or 3 times in a row every now and again. Right? If it's truly random, then that should happen every now and again, right? But Apple was like, well, we can't have that happen because no one's going to like that. So it couldn't be random. They made it less randomly. So here's another situation when seeing a particular pattern might mislead us. Let's take a look. A die with 4 sides colored green and 2 sides colored red is tossed 6 times. Which of the following sequence do you think is more likely? The first one or the second one?
First one.
First one is more likely? Okay. Who here thinks the second one?
Well, from what we've been going over, I think it's the second one.
Yeah, exactly.
Okay.
You have to have a run, right?
Well, you don't have to have a run.
I mean, it's probable to have a run.
Well, it's certainly probable to have runs after lots and lots and lots of tosses, right? But this is only 6 tosses. So the question is, does it still apply? So Leah, what do you think?
I see. Yeah.
I think it's number 2 because it's more likely to land on a green side than a red side.
So a die with 4 sides green and 2 sides red is tossed 6 times. We expect to have 4 greens and 2 reds, correct?
Yep.
And here is a situation of 4 greens, 2 reds. And here's a situation of all greens, correct? So the answer is that this one's more likely.
Yeah.
So Leah, the second one's more likely, not the first one.
That's what I said.
This is the first one.
No, I said the second one.
What was the reason?
The first one.
Okay. So the reason why the second one is more likely is because of the following.
Yeah, I guess.
On the first flip, what's more likely, green or red?
Green.
Green. On the second flip, what's more likely, green or red?
Green.
Green. Third flip, more likely, green or red?
Green.
Green, 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 green. A green on every flip is more likely than this. Now, if I said what's more likely, 6 greens or 4 greens, then the answer is 4 greens are more likely. But I didn't say that. I said is that sequence or that sequence more likely? Because how many ways are there of getting 4 greens? There's lots of ways of getting 4 greens. In fact, you know the answer to this. How many ways are there of getting 4 greens out of 6 reds?
4 out of 6.
No. Well, I'm looking for number of ways, right? It's not
It's not probability. Right.
not probability. How many ways are there? I'm gonna stop sharing for a second. I gotta check something, but think about that question. How many ways are there?
Oh, it's 4 factorial? No, wait. Wait. Is it 6 times 4?
What was the
No.
question?
How many ways are there of getting 4 greens out of 6 flips? So you guys are acting like one chapter's math has no effect on the next chapter's math. Use things that we've learned this semester. You want, out of the 6 trials, you want 4 of them to be greens where order does not matter.
Right.
So this is 6 factorial over 2 factorial, 4 factorial.
15.
Well, the answer is 15. So there's 15 ways of getting 4 greens and 2 reds. So it's more likely to get 4 greens and 2 reds than it is to get 6 greens, but it's more likely to get these than these. Green, red, green, 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 red. It's more likely to get green, 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 green than green, red, green, 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 red, because this one is more likely and this one is more likely. So all greens is more likely than green, red, green, 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 red, which is, again, I think pretty cool. Whoops. Okay, so consider the following arguments for why sequence 1 is more likely than sequence. Oh, okay, so I already did that one. And we did that one. Okay, so down here, last thing. Now, this is one of my favorite things in probability. It's called the birthday paradox. Before I go through it, I'm just going to ask you a question. So I want to go back up here for a second to a blank page. So I'm gonna use it over here. So don't read that page yet. I'm just going to ask you a question here. I'm going to ask 3 questions. Okay, so here's the 3 questions. Number 1, and the first 2 questions, by the way, are not trick questions, but the answers are very, very straightforward. Okay, let's suppose that there's no leap year. So there's 365 days that are possible for each person's birthday. Okay, how many people must be in a room before it is 100% certain that 2 of them have exactly the same day of birth? Not year, just day.
Oh.
How many people must be in a room before it's 100% guaranteed that 2 of them have the same birthday?
366 people.
Excellent. 366 people. Because the first 365 can all have different birthdays, but the 366 has to be a repeat. Right? So you need 366 people in a room before it's 100% guaranteed that 2 of them have the same birthday. How many people must be in a room before there's a 0% chance that 2 of them have the same birthday?
2?
Well, can 2 people have the same birthday?
Say 1 person.
1 person. Once you have that second person, there's already a possibility that they both have the same birthday.
Is that 0 factorial?
No, sorry. I'm not sure why I wrote 0 factorial. That wasn't what I meant. I meant 0%, sorry. How do I?
There's an undo. You can undo instead of clearing everything.
There's a little eraser too. You could just like, there you go.
I tried, that's okay. This is fine. So 0% chance, 1 person. So the question is, now this one's not easy anymore. For there to be a 50% chance that 2 of them have the same birthday, how many people must be in the room?
Is that a half of 365?
That's what I'm asking you. How many people must be in a room before there's a 50% chance that 2 of them have the same birthday? The answer?
2.
183, 182? What?
23, I think it's 23. I haven't actually looked about this in years, but I think it's 23. So,
23.
well, why 23? There's some math involved in that, which we're not going to worry about. But this is called the birthday paradox. Okay, it's a birthday issue that gives you a result which is extremely non-intuitive and very different than what you would expect. Okay, the birthday paradox. Okay, very different than what you would expect. So let's see what they're talking about in the next slide. It says, what most people would call an amazing coincidence typically turned out to be far more likely than they realize. For example, consider the following question. Would you find it surprising if, in a group of 30 people, 2 people shared the same birthday? Now, if I ask people that, I think they will be very shocked that if you had 30 people in a room, 2 had the same birthday. There's so many possibilities for birthdays. January 1st to the 31st, February 1st to the 28th, March 1st, and so on. There's so many possibilities. If I have 30 people in a room, two have the same birthday. Now, let's play a little game here. I'm going to stop sharing for a minute. And I'm going to put my birthday in chat. Not the year. Let's not go there. Just just the day. I'm going to do mine. Okay. And what I would like people to do is to start posting their birthdays. And we'll see if anyone has a repeat, because we got a lot more than 30 people. So if you see your birthday, just shout out. Oh, April 29th. There we go.
April 2nd.
Oh, that's my birthday.
And a couple April 2nds, right? How many people were in the room right now? Is there a way to count?
37.
37 people. So out of 37 people, we have at least 2 repeats, if not more. I saw April 29th and I saw April 2nd. And of course, just so you know, mine, October 24th is like next week. Birthday presents are accepted. Anyway, so let's go back.
Credit.
What?
For extra credit.
You want to give? Wow, okay, that's probably worth it. Okay, anyways. So most students will be surprised, reasoning that the 30 people could have any of 366 possible birthdays. So the probability of 2 having the same birthday should be small. In fact, it's better than 70%. And the reason it's so high is there's so many pairs of people. Any 2 people could have the same birthday, right? 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, 1 and 7, 2 and 1, 2 and 2, 2 and 3. Don't look at 30 people as 30 individual people. Look at them as pairs of people. 30 people have lots of pairs. In fact, we can compute. How many pairs are there in 30 people? Let's do that.
900? No.
Well, no. Let's think about it. If I have 30 people and I want to know how many pairs there are, that's 30 people. I want to pick 2 at a time. I want pairs. And the order does not matter. So this is a combination. Right? Picking 2 people at a time from 30 where the order does not matter. That's going to be 30 times 29 over 2. That's going to be 59, 29, 290. That's going to be 435. Or 425. I think 425. Did I do that right?
The 29 times 15. Hold on, wait.
Yeah, what's 29 times 15?
435.
Oh, I was right the first time. I don't know why I second guessed myself. So there's 435 pairs of people, 366 possible birthdays, which means it's very likely that 2 of the people have the same birthday. And in fact, it says compare the birthdays of each members of your class, including the instructor. The easiest way, well, who cares about easy way? We did it pretty easy. And we saw that 2 people had the same birthday, so not exactly what you expect. Are there any matches? Yes.
There's also 2 people on November 9.
So there's 3 pairs. Crazy talk. All right. Anyways, we can skip the last. I'm tired. I want to go to sleep. So we don't
Hey, bye.
Okay, that was a little uncalled for, but okay. Just really a little kind of hurtful at least, but that's okay. I get it. I feel that way also.
Tired too.
Yeah, I get it. Me too. Okay, so so if you haven't had the quiz in yet, do that. And we should probably have a quiz next week.
No.
Yeah, we got to have quizzes and stuff. They're important, and I don't want to get fired. So
On what chapter?
how's chapter 7?
What?
What? That's the last one we did. What's the what?
I haven't even done chapter 7 yet.
We just did chapter 8.
Okay, chapter 7.
Can we do chapter 1?
No, chapter 1's over and long done with.
You better put up those homework solutions.
Oh,
Worth a shot.
okay. Homework solutions, fine. I'll do that. Better. Okay. Extra credit. What do I care about your birthday for? My birthday is the one that should get extra credit. Anyway, okay, so yeah, I'll put up the solutions. Probably not today. I'm too tired. I'm gonna go to sleep. But
Do it now before you go to bed.
oh my God. Fine, jeez. No, she's right. I should. If I don't do it now, I'll never do it. Okay.
Yeah. I'll be
Okay.
emailing you. It'll be a big scene.
Wow. Jeez. Okay. What a big scene. Okay. All right. I'll do that now. Fine. I'll do that now. Right now. What is that?
Yay!
What is
Thank
that?
you.
Just do it. Oh, Tolaire, you're funny. Okay, I'll do it now. Okay. Okay.
Thank you.
Thank you.
All right, guys. Thank you. Okay. Have a good night.
Later,
I'll see you
Teach.
guys on Wednesday. Okay. Okay.
Thank you.
Okay. Bye bye. Okay. All right. You're welcome. You're welcome. You're welcome. Do I lose point for being late? Mia, when did you arrive?
Like 7:10.
Well, it's not that you lose a point, but in fairness, I do have to mark you as late.
Okay.
I'm sorry.
Did you see his present, Professor?
Oh yeah,
Lorena?
you're new who am I talking to?
To Lorena.
Who? Talar?
Lorena.
Oh no, you were here on time. I got you right away.
Okay. Just making sure.
Namira was late. I got her. Okay. Yeah, it's all fixed. Okay. All right, guys. Have a good night. Okay. Bye.